So we're gonna wrap up chapter 5 today up, and we'll get into chapter 6. Last item from the floating point. So we can add two floating point together. So you need to go through these steps. First, we want to extract the exponents and the fraction bit, and then we're going to compare exponent. That's the key thing. 7.5 times 10 to the 2, 0.5 times 10 to the 1. If the exponents are different, we cannot just add and say it is 8.0. This is wrong, right? So we need to make these exponents to be the same. That's the key thing in here. Let's copy down. Let's add these two numbers. So first thing we want to do, we want to put those into binary numbers, right? So I'm going to put those two binary numbers. Then it's going to be something like this. So we have a 3 for the blue part, 0011, F 1111, C 1100, and the rest is going to be zeros. 405, the blue one is 0100, which is 40, and red is 50101. You can put first two zeros and dot 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 and last two zeros. Just don't forget when you give answer back to me, has to be 8-bit hexadecimal bit. You don't have to put all those zeros and you don't have to count them all. As long as it's a 32 bits, you know that, and then convert that into hexadecimal should be 8-bit of hexadecimal number. Now we need to put that into IEEE 754 floating point format. So if we do first bit is the sign and then 8 bits. So you can just highlight it. First bit is the sign and you count on 8 bits and that is the exponent and the rest is going to be the fractions. We have these two numbers and then first number we have a sign bit as a 0, exponent is 127, fraction is a 0.1. Second number, sign bit is 0, exponent is 128, fraction is 0.101. So the first number we can write as a 1.1 times 2 to the power of 0. 127 is our magic number. Second number is 128, so 1.101 times 2 to the power of 1. Again, this 1 point, this 1 is there. It's a hidden, but it's there. It's not from any of the number we have. So now we need to kind of move left or right for this decimal to match up this. So compare exponents, 127 and 128, they're not the same. We typically match with the smaller one. But for this class, if I test you, you forget about match to smaller one, you match to bigger one, that's fine. So if you match it to smaller one, 1.1 to the 0, and we move the decimal to the right by 1, so 11.01 to the 0, and then add them up, 100.11 times 2 to the power of 0. But if you move to the larger number, at the end, we're going to get this. So either one, but smaller one is the typically we do. We have 10.011 times 2 to the 1. We need to make it to normalizer or put it into scientific notation, move decimal point to the left by 1. So we need to increase the power by 1. So 1.0011 times 2 to the power of 2. And now our magic number is 127 plus 2 is 129. Put it into the exponent portion, and the fraction is going to be 0011. And then you combine 4-bit at a time. So this is our hexadecimal answer. Next topic is a sequential building block. So first thing, the book talks about the counter. Counting 0 to 3, go back to 0. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. That's the counter. 2-bit counter. We can have a 3-bit counter, 4-bit counter, 5-bit counter. Okay, this is the implementations. And then shift registers. So we already talked about logically shift left and right, and then arithmetic shift left and right. So that's the kind of implementation and the symbol. Memory arrays. So chapter 8, whole chapter is about the memory. So we're going to revisit this memory component, and chapter 8 will talk about how to design a cache. So I'll give you a kind of overview of memory in this chapter. So there are three common types: DRAM, SRAM, and RAM. In the memory, we have to have address. The address is just like a mailing address. I'd like to deliver a mail to you without the actual address. I cannot do that. So we need to have exact location of the memory, and then we can produce the data. And it is a two-dimensional array, and each bit cell stores one bit. When you see this memory address n and array and data m, 2 to the n rows, okay, m column, depth is this guy, width is this guy, array size. We have memory here. This is our address. Let's say address is 4 bits. How many rows I can have? Start with the 2 bits. If memory address is 2 bit, 4 rows. Exactly. And then this width, let's say 4 bits. What's the size of this memory? All right, so 16. In the ARMS architecture we're going to talk about, okay, is all 32-bit registers. So let's say width is the 32-bit. Now memory address is now 4 bits. How many rows? 16. So the size of the memory in this case, 2 to the power of 4 by 32. That's how we calculate the size of the memory. So if we know the number of bits for the address, we can calculate depth. And then if we know the width of this memory, typically the register size for ARM again, for this class is 32-bit. So that's what it says, all of this. And this is width, depth, and then the address. So now if we have 2 to the power of 2, because 2-bit for the address, so 2 to the power of 2 by the data size coming out from here. So for this case, it's 32-bit coming out. That is the 3 bits. So that's the size of the memory. You do it, calculate this. You have a 10-bit address and 32-bit data. So the width is now 32-bit. Memory address is 10-bit. So what's the size of this memory? Your answer should be in kilobit. Okay, good, good, good. How many bits of address? 10. So we need to write 2 to the power of 10 by 32. Now, for us, 2 to the power of 10 is what? 1024? That is what? You don't have to get to 1024. This is our kilo, 32 kilobits. Book talks about the word line, all of this, and I'm not going to worry too much about it. So output is 0001. When the address is 00, output 01, 0. So based on the address, we're going to take only 1 bit in this case. And then if you have 3, then based on the address, you're going to take 3 bits. If you want to calling memory or location 10, we're going to get 100. Random access memory, read-only memory, RAM and ROM, volatile versus non-volatile. This was the true in the back then, not anymore. Okay, not anymore. RAM versus ROM. And typically, RAM is cheaper, and we have a DRAM and SRAM. Now, let's look at the RAM. It's actually, we can design the contents of the RAM. Let's say you are given something like this, 00 in the memory location. We have a 0, 1, 1. You just need to have a 0, 1, and 1. When we have a 1 and 1, we just connect this. You can use closed dot or X to indicate that this data, look, the memory location of 00, output should be 011. Similar way, 01, 110. Location of 10, we have this, we have that. That's very straightforward. Now, when you express your answer, the D0 is A1 prime, A0 prime. How? When you read the D0, we need to read this plus this plus this plus this. This is 0, this is 0, this is 0. This, how you read it? As a mean terms. Reading input, if it's 0, it's a prime bit. If it's 1, it's not prime. Since this guy has a 0 and 0 for first two, so A0 prime, A1 prime. Make sense? For the second one, D1, we need to read this. Tell me, what is it? Right? A1, no prime because it's 1, 1. A1 and A0, right? Plus 0 plus this guy. Say it. Exactly. A1 prime, A0. This guy. Okay. So that's that. Now, here's the Boolean algebra. So once you have this, we can combine this guy. So factor out a1 prime. You know what I'm talking about? Maybe, maybe not. So once we have that, plus 0, we don't have to have it. Let's say with these two, we have a1 prime, factor out a1 prime. Now we have a0 plus a0 prime. And this guy, a0 plus a0 prime equals to what? 1. So that's a1, a0 plus a1 prime. How we combine this? Kim's rule. We talk about Kim's rule, right? In the Kim's rule, a plus bc equals to a plus b and a plus c. That's the Kim's rule. So if we do this, a1 plus a1 prime and a0 plus a1 prime, this will give us 1. So that's what we have. D2, we have a1 prime, a0 plus a1 times a0 prime. That is the definition of XOR. So now we have expression, not the table. X equals to AB and Y equals A plus B, Z equals AB prime. X is what? A and B. So A is 1, B is 1. So this is the 1. Done. Z, A, B prime. A is 1, B is 0. A is 1, B is 0. Done. So if you have these two letters, you can just interpret that as a mean terms and put the mark X or 0. Done. Now for this guy, A plus B, we have A or B, right? So for Y, whatever this side is A and B, whatever we have A, gonna mark it. A is 1 for these two, and B is 1 as well. B is 1, this guy and this guy, the top one. We already did it. For this expression, it's gonna go with these 3 dots. Is this the only way to go from here to here? Not really. To prove this, we can use Boolean algebra again, and we say, A, I'm going to add B plus B prime, which is 1. And for B, I'm going to add A plus A prime, which is 1. And then AB plus AB prime plus AB plus A prime B. We have AB, same thing. So at the end, we're going to have this, which is exactly those 3. This is one of your homework problems. So similar way, we need to do this. So I'm going to do 1 or 2 only. The rest, I want you to do it. Let's do Y. Y equals to what? AB plus A prime D. And then since we have a 4 A, B, C, D, so we have 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to just do only Y. So what we can do, one thing is A, B, we're missing C and D. So just like what we did, A, B, and C plus C prime, and then A, B, D plus D prime, and then combine all of those. It's going to be really long process. I'm not going to do that. Instead, I will look at 2 separately. So we have A, B, meaning what? A equals to 1, B equals to 1, C and D. What happened to C and D? We call it don't care condition. B and C is a don't care. So I'm going to look at the A and B. They are 1. Where is it? A and B is the 1 for these 4. That's the only 4 we have A and B as a 1. Or is or. We're just adding them. Now A's prime D is 1. So it's going to be 0. Don't care. 1. So as long as we have a first one 0, last one is 1, we're going to select it. 0, 1, 0, 1, 0, 1, 0, 1. That's it. How about Z? Let's do Z real quick. Z equals A plus B prime. So we're going to cover every single one with the A equals to 1. A equals to 1. These bottom 8, and b equals to 0. Second number is 0. We have 0, 0, 0. We already covered that. And then first 4. Now you should be able to do x a similar way. So logic array. So it's the logic array as an example. We have data 1, 0. You read through it. Last one is only 1. So it's a A1 bar, A0 bar. So it's very similar. The last item from Chapter 5 is a PLA and FPGAs. PLAs stands for Programmable Logic Array, combining AND gates and OR gates together. Field programmable gate arrays, we have that. So we're gonna just look into PLAs only. So for the PLAs, we have AND arrays in the middle. So we have A, B, and C. There's A is 1 line, A is 0 line, B is 1, B is 0. And then if you need A bar, B bar, C, we're going to take the A bar, B bar, C in the AND gate, and we're going to combine them using OR gate. That's what it is. And sometimes we use PLA without showing this AND array or array, because we know this is AND arrays in here, OR arrays in here. So this representation and this representation are the same.